The spin directions of electrons in a typical superconductor are generally opposite within a Cooper pair. In other words, the two electrons forming a Cooper pair have spins pointing in opposite directions, as described by the BCS theory. This phenomenon arises from the attractive interaction between electrons with opposite spins in the superconductor. However, not all superconductors exhibit this behavior. In the case of chiral superconductors, it is known that the spins of electrons forming Cooper pairs are aligned in the same direction. Chiral superconductors remain mysterious materials, and the principles governing their behavior are not fully understood. Therefore, the spin directions of electrons within a superconductor can vary depending on the type of material. For conventional superconductors, it is commonly known that the spins of electrons forming Cooper pairs are opposite to each other. In the case of conventional superconductors, the spin directions of electrons forming Cooper pairs are generally opposite. Therefore, electrons with the same spin direction are not known to form Cooper pairs in these materials. While it is acknowledged that chiral superconductors exhibit Cooper pairs with electrons having the same spin direction, the underlying principles of these mysterious materials have not been fully elucidated. Consequently, it remains uncertain how electrons with the same spin direction would behave if they were to form Cooper pairs in chiral superconductors. If electrons with the same spin direction were to form Cooper pairs, one possibility could be the combination of their electric charges, resulting in the formation of a positive charge, possibly resembling a proton. However, it is challenging for freely moving electrons to merge with protons, which are particles confined within atomic nuclei. Another conceivable scenario is that, even if electrons with the same spin direction were to form Cooper pairs, they might interact with Cooper pairs having opposite spin directions, returning to their original state. Nonetheless, whether such phenomena actually occur remains to be conclusively established. When electrons combine with electrons, they can form a positron. When electrons combine, two positive charges are produced, resulting in a positron. This process is known as electron-positron annihilation. A positron is a particle with a positive charge. Electron-positron annihilation is a natural phenomenon that occurs in the natural world. It takes place in space missions or nuclear reactions. Additionally, after the creation of electron-positron pairs, their annihilation can occur shortly thereafter. The process of electron-positron annihilation can be expressed by the following equation. \e caret plus plus e caret backslash right arrow backslash gamma plus backslash gamma backslash. Here, e caret plus backslash represents a positron, e caret backslash represents an electron, and backslash gamma backslash represents a photon. Electron-positron annihilation is a process where the masses of both the positron and the electron disappear. Therefore, to satisfy the law of energy conservation, two photons must be generated. Electron-positron annihilation is the opposite of the interaction between a proton and an antiproton. When a proton and an antiproton collide, an electron, a positron, and two photons are generated. The phenomenon of electron-positron annihilation is significant in particle physics. It allows for the measurement of the mass of a positron. Furthermore, electron-positron annihilation is employed in the study of space missions and nuclear reactions. The combination of two electrons can result in a positron. Since electrons have a charge of -1, and positrons have a charge of +1, the combination of two electrons results in a charge of 0. When a neutral neutron is added to this state, it forms a positron. This process is known as pair annihilation. Pair annihilation occurs when a particle meets its antiparticle, annihilating each other and creating two new particles. In the case of electrons and positrons, this corresponds to pair annihilation of particle-antiparticle pairs. Pair annihilation is a common phenomenon in nature. It occurs when spacecraft collide with the atmosphere, during nuclear fusion reactions on the Sun's surface, and in various other situations. However, the combination of two electrons is very rare. This is because electrons are freely moving particles, and for them to undergo pair annihilation with a positron, they would need to move at very high speeds. Additionally, the neutral neutron involved in the process requires very low temperatures for pair annihilation to occur. Nevertheless, in the context of superconductors, if electrons with the same spin direction form Cooper pairs, there is a possibility of two electrons combining to form a positron. This is due to the high speed at which electrons forming Cooper pairs move, especially in the case of chiral superconductors, where Cooper pairs with the same spin direction may be stable, making positron formation more feasible. Therefore, investigating the existence of Cooper pairs with the same spin direction in superconductors is of crucial importance for studying the potential formation of positrons. Chiral superconductors are a type of superconductor characterized by the alignment of the spin directions of electrons forming Cooper pairs in the same direction. The principles governing chiral superconductors remain enigmatic, and while proposed in the 1980s, it took a considerable amount of time for experimental discoveries to be made. In 2008, a Japanese research team first identified materials with the potential for chiral superconductivity, and in 2018, a US research team experimentally confirmed the existence of chiral superconductors. Chiral superconductors exhibit the following characteristics. The spin directions of electrons forming Cooper pairs are aligned in the same direction. The direction of the superconducting current determines the direction of the current flow. Their interaction with magnetic fields is peculiar. Chiral superconductors hold potential applications in various areas, including enhancing the performance of superconducting computers, generating Majorana fermions, developing new forms of superconducting memory. While research on chiral superconductors is still in its early stages, their diverse potential applications suggest that future studies will be actively pursued. The principles underlying chiral superconductors have not been fully elucidated, but several hypotheses include 1. Spin-orbit coupling of Majorana fermions. The spin and orbital angular momentum of Majorana fermions are coupled, causing Majorana fermions with the same spin direction to move in a specific direction. This phenomenon is known as spin-orbit coupling, and it is believed to play a role in determining the direction of superconducting currents in chiral superconductors. Principle based on interacting magnetic moments. Electrons possess a spin-associated magnetic moment. If the interaction between electrons is strong, their magnetic moments may align, influencing the direction of the superconducting current in chiral superconductors. As research on chiral superconductors advances, revealing their underlying principles, it is anticipated that they will find diverse applications in various fields.